This is Honors Geometry section 5.1 on bisectors of a triangle. And so far we've dealt with two kinds of bisectors. We've had bisecting a segment when a line or segment or array or even a plane intersects the midpoint of a segment. And we've also had angle bisectors, which split an angle into two equal angles. And today we're going to be expanding on those, first with the segment bisector. And when a segment bisector is also perpendicular to a segment, that's when we call it the perpendicular bisector. So in this first little argument here, and I'm calling it an argument rather than a proof because I'm not going to formally put it into proof form, but if AB is the perpendicular bisector of segment DC, then make an argument that segment AD is congruent to segment AC. So first of all, if it was a full-up proof, I'd say that I have the given. And if AB is the perpendicular bisector, then by the definition of bisect, B is the midpoint of segment DC. And with the definition of midpoint, then the segments DB and CB would have to be equal to each other. The perpendicular part of the perpendicular bisector means that angle 1 and angle 2 are right angles. And that means we know they're 90 degrees, therefore they're equal to each other. So those angles are equal to each other and right angles. Segment AB is equal to itself with a nice little reflexive. Therefore, using side angle side, we could say that this yellow triangle is congruent to this blue triangle. Now, the reason why that's significant is then because of CP/CTC, we could conclude that segment AD is congruent to segment AC, and that's what we're trying to prove in this one. Now, the thing about this little argument or proof that is made right here is I use point A. I could easily put a point right here as well and say that this point is also equal to points D and C, and we'll explore that a little bit further. So bisectors of a triangle is the first one, a perpendicular bisector. All right, so if I have a triangle like this, and I want to do the perpendicular bisector of one of the sides, I find its midpoint, draw in the perpendicular, and there we have one of them. Now the perpendicular, or each side of the triangle has a perpendicular bisector, so I could find another one, I could find a third one, and those are the perpendicular bisectors. Now the thing about these perpendicular bisectors is that they do not necessarily go through any of the vertices of the triangle. More about the triangles in a minute. Perpendicular bisector theorem. So I have this segment AB, and if I have the perpendicular bisector of it, so we'll say line L is the perpendicular bisector of segment AB. That means it is bisecting it, so it hits the midpoint, so these segments are equal to each other. We also have that right angle. And what this perpendicular bisector theorem is going to say for us is that if a point is on the perpendicular bisector of a segment, then it is equidistant to the endpoints of the segment. Now, normally I'd want you to, we'd work through this and come up with that idea together, but I'm just going to straight up tell you that this is our perpendicular bisector theorem. And not just the definition of a perpendicular bisector. I've used the definition of a perpendicular bisector to make these markings. What I'm saying is if I could pick any point on line L, either to the left, to the right, close to this intersection point, far away from the intersection point, I could pick any point such as this point C, and I believe that the distance from B to C is the same as the distance from point A to C. I believe that those are equal to each other. To prove that, I'm using those original markings that I have in blue, and then reflexive, this segment is equal to itself. And then I can see very nicely, like we had it before, that this green triangle must be congruent to this gray triangle because of side angle side, and then CP, CTC, CA is congruent to CB. It doesn't matter where that point is. If a point is on the perpendicular bisector, whether it's that point C, if it's this point, if it's this point, if it's this point, even if it's that point, all of these points are the same distance to A as they are from B. This is the perpendicular bisector theorem, not the definition. We also have a perpendicular bisector converse that's going to be true. So if you remember the converse, that's when you switch the hypothesis and conclusion around. So if a point is equidistant to the endpoints of a segment, then it is on the perpendicular bisector of the segment. So this is, normally we reserve biconditionals for definitions. That's why we're not calling this just like one single biconditional. What I'm saying here is if I have some point, like this point C right here, and if I know that BC is equal to AC, then I believe that point C is on the perpendicular bisector of segment AB. A little bit trickier to prove because we're going to have to draw in an auxiliary line. And through point C, I could draw an infinite number of lines. Through point C, I could draw an infinite number of lines that also intersect segment AB. But I'm going to choose one in particular. I'm going to choose the segment that goes through point C and is perpendicular to segment AB. So I can draw that. I'm not putting any other special requirements. I'm saying I want to draw in that perpendicular. By drawing in that perpendicular, it creates two triangles. With the reflexive, I know this segment equals itself. And then we have these two triangles. How could we prove these two triangles congruent to each other? Well, we don't have a side angle side this time. However, we do have HL. We have hypotenuse leg. So the triangles are congruent to each other, which means CPCTC. In other words, this segment must be congruent to this one. If those segments are congruent, then they're equal. If they're equal, then this is the midpoint. If this is the midpoint, then this is a bisector, meaning this red segment was not only perpendicular to AB, it also bisects AB, which makes it the perpendicular bisector. So if any point, like point C or another point out here, if this point was equidistant from points A and B, it would also be on this perpendicular bisector. Concurrent lines are lines that intersect with each other, and two lines intersecting isn't a big deal. In triangles, we're going to be looking at three lines intersecting each other, and when they intersect, we call them a point of concurrency. This would be a point that has three or more lines intersecting at that point. And our first concurrent point is called the circumcenter, and it's formed by the perpendicular bisectors of a segment. And we'll look at this special part here in a second. But here's my triangle, nothing special about it. From, I'll call this segment AB at the bottom. Through that point, I'm going to draw in my perpendicular bisector. So I'm saying it's the midpoint of that segment is perpendicular to that segment. So here's one of my perpendicular bisectors. I'll go to segment BC, say I think the midpoint is about right there. And as best I can, draw in a perpendicular that goes through it. So there's our second perpendicular bisector. And now over to segment AC, I think the midpoint is about right there. And through that point, as best I can, I want to draw in another perpendicular. And what happens is that those three perpendicular bisectors all intersect at one point, and that point is called the circumcenter. And the circumcenter is, like, those three are always going to intersect. The circumcenter is always going to exist. Now, what's special about the circumcenter, let's choose a color, there we go, is that, for instance, this point is on the perpendicular bisector of segment AB. And if I scroll back up here before, remember that if a point is on the perpendicular bisector of a segment, it's equidistant to the two endpoints. So using this perpendicular bisector theorem, I know that the distance from this point to A is equal to the distance from this point to B. In other words, this segment has to be equal to this segment. Furthermore, I have this red perpendicular bisector. This point is on the perpendicular bisector of segment BC, which means this point is equidistant to C and B. So not only is this segment equal to that segment, this segment is also equal to this one. which means all three of those segments are equal to each other. So what we've just found is the one point that is the same distance from all three of the endpoint or all three of the vertices of a triangle. So what is special about this circumcenter is that it is equidistant to the vertices of the triangle. Here's another drawing of what a circumcenter would look like. So I have a perpendicular bisector, perpendicular bisector, a perpendicular bisector. They're all intersecting at that point G. And I know there's no markings on those, but I'm just telling you that the green, the gray, and the yellow, yes, they are perpendicular bisectors. And what that means to us is then that this segment is equal to this segment is equal to this segment. All three of those are equal because this circumcenter is equidistant to the vertices of a triangle. All right, the next kind of bisector we're going to look at is the angle bisector. So I have this angle ABC, and BP is the angle bisector of that angle, which means that this angle is equal to this angle. And point P is just some point that's on the angle bisector. From point P, I'm going to draw in a perpendicular this way, and I'm going to draw in a perpendicular that way. And if you recall, the distance between a point and a line is the shortest distance, and that's going to be the perpendicular distance. So PR is the distance from P to this side of the original angle. So again, here is our original angle that was being bisected. So PR is the distance to this side of the angle. PS is the distance to this bottom side of the angle. And what I'm noticing is that we created two triangles again. There's this green triangle and there's this gray triangle. With the reflexive, this segment is equal to itself. And then I can realize that, hey, you know what? This green triangle up here has the same angle side as the triangle down here, angle side. Therefore, the triangles are congruent to each other, which means that CPCTC, segment PR, is congruent to segment PS. That leads to another theorem. The angle bisector theorem would say that if a point is on the angle bisector of an angle, then it is equidistant to the two sides of the angle. So I have this point P. I could just as easily say, hey, I have a point right here. If I draw in this perpendicular distance, and if I draw in this perpendicular distance, those two perpendicular distances would have to be equal to each other because of the proof that I just did. So that's our angle bisector theorem. Notice we have another converse. So can you anticipate what the converse is going to look like, knowing this is the theorem? What would the converse be? How about if a point is equidistant to the two sides of an angle, then it is on the angle bisector of the triangle. All right, why would that work? Let's see. Here is some angle. And I'm going to have a point. Let's put it like right here. This point is the same distance to this side of the angle as it is to that side of the angle. So this is the given. This is the hypothesis part. And I believe that this point is on the angle bisector of that black angle. Now, how would you prove that? Once again, with the converse, we're going to have to draw in an auxiliary line. We're going to draw in the line that goes from this vertex of the angle, this point, and passes through that point. And by doing that, we created two triangles. We create this blue triangle and we created this yellow triangle. Can you see how we would prove them congruent to each other? Specifically then, reflexive, this segment is equal to itself. Therefore, by HL, the triangles are congruent to each other. After the triangles are congruent, CPCTC, this angle is congruent to that one. Because the angles are congruent, then they're equal. Because the angles are equal, then this green segment, by definition, must be on the angle bisector. So that is the angle bisector converse. Our next concurrent point is called the incenter. The incenter is formed by the angle bisectors of a triangle. Incenter is formed by the angle bisectors of a triangle. So here is my triangle. I'll try to draw this as good as I can. Oops. So from this vertex, I'll draw in an angle bisector. This angle is equal to this angle. And I'll draw in another angle bisector. How about this one at the top? As best I can, try to bisect it. So there is another one. We have this point so far, and this point is on the angle bisector of this original big angle A right here, which means by the angle bisector converse, or the theorem, sorry, this segment must be equal to this segment. Again, here is our angle. It's being bisected, so this point must be equidistant to those two sides of the angle. Additionally, since this point is on the angle bisector of this green angle, that means that it's equidistant to the two sides. So if I draw in my perpendicular over here, this segment is also equal to those other ones. So what we have here then is that these three segments are equal to each other. In other words, from this incenter point, the distance to the three sides of the triangle must be the same. And there's one more angle bisector I could draw, and it would look like this. It has to go through that same point. This angle equals this one, just like this angle equaled that one earlier. And we have our incenter. What is special about it? It is equidistant to the sides of a triangle. Scroll down a little bit further. Here is a scalene triangle. It looks like it is slightly obtuse. Angle bisector, angle bisector, angle bisector. They intersect at point D. So this is our incenter. And what we're saying is with this definition, or the special property of an incenter, is that DE is equal to DF is equal to DG. All three of those segments must be equal to each other. Let's get into some examples because that's a lot of information so far. It says determine whether point A is the incenter or circumcenter in each diagram. So my first one, point A, we have an angle bisector, an angle bisector, an angle bisector. By definition, that means point A must be the incenter. Example 2. If I look at the markings, this is a perpendicular bisector, perpendicular bisector, perpendicular bisector. They're coming together at point A. That is the definition of a circumcenter. And our last one here, perpendicular bisector, perpendicular bisector, perpendicular bisector. So point A, once again, must be the circumcenter. And one thing to notice about this one is for the first time, we have this concurrent point. The circumcenter is outside of the triangle. And more on that later, but it can happen that in certain triangles, the circumcenter can be located outside of the triangle. I'd pause the video for a minute, put the given information on this one, try to work through the problem. When you're ready, hit play again, and you can see if your answers are correct. Let's see, so some of our information here, since this whole angle is 30 degrees, this is trying to show that this angle is being bisected, which means that this is going to be 15 degrees, 15 degrees. This angle was equal to that angle, also being bisected, so we have another 15 degrees, 15 degrees. The first thing we're asked for here is the length of AG. All right. Angle bisector, angle bisector, angle bisector. That means this point G is the incenter of the triangle. What's the special property of the incenter? It's that these segments, the distance to all three sides of the triangle must be the same. So each one of those segments is 5. if I'm trying to find AG, here's my triangle. I have a 5 and a 12 for the lengths. And it's a right triangle, so Pythagorean theorem, 5 squared plus 12 squared equals AG squared. 5 squared plus 12 squared equals AG squared. Solve that. AG is going to be equal to 13. Next question, angle GCF. Ooh, I've already got that one at 15 degrees. Measure of angle ABC. So 30 degrees, 30 degrees. Together that's 60 degrees, which means there's 120 degrees left for that angle. Drawing is definitely not to scale. All right, here's the next one. So for this one, perpendicular bisector. Point B then is the circumcenter. If we draw in this segment DB, that creates this right triangle. And I see that there is a 6 because that's half the 12 and a 4. To figure out this length, another Pythagorean theorem, 6 squared plus 4 squared is equal to DB squared. So DB is the square root of 52. I'll break it down if I need to. The question is the length for AB. Here's again is where I need to understand what a circumcenter is. A circumcenter is equidistant to the vertices. So BD equals BA would also be equal to BE if I drew it in there. So since DB is square root of 52, AB is also equal to the square root of 52. So it looks like I need to break this one down. AB is 2 root 13 units.